Hello everyone, and welcome to part 4 of our review video series. Right now we're going to be working on waves and sound. So mechanical waves and sound. So let's get right started. You can see I've been doing this for a little while because apparently I can't speak English anymore. Alright, so a string has a mass of 0.05 kilograms and a length of 1.3 meters. You'll notice that I put it in kilograms and meters for you already. That is me being nice. Don't expect that on the test. And a tension of 75 newtons. What is the fundamental frequency that you would hear when the string is plucked? Alright, so let's just start with A. We'll worry about B and C later. So it has a mass of 0.05 kilograms and a length of 1.3 meters. Well, the equation we're going to need here if we want to know what the fundamental frequency is the equation for the frequency of the nth harmonic for a string, which is going to be V over 2L, excuse me. N times V over 2L, where N is the number harmonic, V is the speed of the wave in the string, and L is the length of the string. So for the fundamental, N is equal to 1. Alright, for the fundamental. So F1 is going to be just V over 2 times our length, which is 1.3 meters. But we have to figure out what V is, the speed of the wave in the string. It so happens that we have the means to do this because we were given the mass, the length, and the tension. If you'll recall, the speed of a wave, that looks like it says speed, sped of a wave on a string, which you have in your equation sheets, is V is equal to square root of force tension over mu, which is the linear density, the linear mass density, which is everything we need. So we've got the square root of our tension, which we said was 75 newtons, over the density, which is going to be the mass over the length. So it's 0.005 kilograms in kilograms per meter over 1.3 meters. So plugging all that in, taking the square root, you get that the speed of the wave is about 140.5 meters per second, which is exactly what we plug in here. So when we do that, 140.5 divided by 2 meters per second, divided by 2 times 1.3 meters, gives us about 54 hertz. Pretty low. It's probably a bass, I'd imagine. I wonder why that is. 54 hertz for the fundamental frequency. Alright, so moving on to part B. So part B is asking us, how long would an open tube have to be to produce the same frequency as the string above? For the fundamental, I'm going to say, and assume that the speed of sound is 340 meters per second. So if you recall, for an open tube, the function or the equation is actually the same. So we use the same frequency equation for the open tube, only this time V is not the speed of wave on a string, it's the speed of sound. So what we want to do now is we want to rearrange the equation to solve for L. So what I'm going to do is I'm going to take L, I'm going to multiply both sides by L, and then I'm going to divide both sides by Fn, which is just going to be 1, right, because we're looking for the fundamental frequency. So multiply both sides by L, divide both sides by F, we get L is equal to 1 times V sound over 2 times F1 times the fundamental frequency. We know what the fundamental frequency is from before, so we can go ahead and plug that in. So we have 340 meters per second over our 2 times 54 hertz, which gives us a length of, interestingly enough, 3.14, well, 15 about. Let's call it 15 so we don't get the pi reference confused. 3.15 meters is the length of our tube, of our open tube that would produce the same frequency as this string does. And last, for part C, scroll down. You now put a cap or otherwise close one end of the tube you determined in part B above. What is the new fundamental frequency of this open closed tube? So we're just looking at the open-closed tube now instead. So the open-closed tube does have a different equation for it, again, all in your equation sheet, but Fn is equal to 2n minus 1 times v over 4L. So we can again assume that the speed of sound is 340 meters per second. That's this. Again, because it's a tube, it's the speed of sound we're looking at, not the speed of a wave in a string or otherwise. N is going to be 1 again, because we're looking at the fundamental frequency. So this whole part of the equation just becomes 1. 2 times 1 is 2, minus 1 is 1. And that'll give us our fundamental. So F1 is equal to the speed of sound, which is 340, over 4 times our length, which we said was 3.15 meters, which will give us 26.9, or let's call it 27. 27 hertz, even lower. Those of you that did instruments, that did the panpipes, like half of you, will have noticed that if you closed off the panpipe, it made a lower sound than the open panpipe. And if you look carefully, actually, you'll notice that it is twice the frequency. Or sorry, it's half the frequency. It's actually an octave apart, right? So 1 octave is when you double the frequency. So if we double 27, we get 54, which is the frequency of this pipe. So if you close off a open tube and make it an open closed tube, it actually lowers the frequency by 1 octave. Interesting. All right, there we go. That's number 4, and meet me again next time for optics. Almost done. See you soon.